Thank you very much, Matt. So I try my best. Would like to infrastructure maintenance issue based upon my experience in this program leader. So my background is civil engineering and the bridges, more specifically dynamics control and monitoring, and all these bridges are involved. Also, the bridge painting is one of my hobbies. So today's topic is more wide infrastructure. We have various kinds of infrastructure. Can I have a pointer here? Yeah, various kinds of infrastructures. This is in Tokyo and Japan. But let's look at the Asia, Bangkok, compared to just 24 years difference, but completely different. We have a bunch of the infrastructure or bridges. Bangkok, Asia, and China is probably more. Shanghai, Sutton Bridge, and this is a photo, 2008, Shanghai, 2016 or so. You can see so much different, even Shanghai. Back to Japan, we will have an Olympic game next year, but we had Olympic in 1964. That's about 55 years ago. And that time we built a high-speed train, urban expressway, and they are still using, of course. And this is urban expressway, and it carries millions of vehicles a day. Even though the structurally degraded, damaged a little bit, but the value of the structure is more increased, and this is a good example of the nice infrastructure. But let's look at this automobile, Toyota, Nissan, TV, radio, all these gone, right? No one uses this anymore. So it's a big difference between long-term infrastructure and like cars and a TV. So this is when I was a kid, she's a very well-known and attractive actress. And she's still good shape because good maintenance. So good maintenance makes a difference. One professor, Uzawa, he studied in the US, Professor Chicago, and returned back to University of Tokyo. He's a very close, he was not, but he was close to the Nobel Prize in economics. He proposed idea of the concept of social common capital. And according to his definition, of course, this is an asset for the society, asset for the society, and an asset for the society. So public and not private. So he classifies three types: nature, water, air. No one can own that. And civil infrastructure, like we are dealing with. And also social systems, rules, which apply to everybody, like medical or education. These three are very important social common capital. So our infrastructure is one of them. So importance, he stressed that importance of maintaining these capitals in the good shape is very important to our rich, wealthy life. But of course, our physical structure gets old and many problems. This is I just got a copy of this video animation. That's very well known, probably the biggest accident in the world in a bridge accident, 1967.
The road hung from a simple, elegant chain design made possible by a new type of high-carbon, high-strength steel.
And this is like a chain. This is a chain. Of course, no one inspect. No one take care of it for many years, 30 years, 40 years. And one day, Friday evening, the bridge collapsed. It will show.
The circle of the eye-bar where the steel was at its thickest.
So it's a Friday evening, so many cars, and 46 people are killed, lost. So this is animation, not real video.
The bridge was falling.
So this is an accident, and we really realize that we need inspection, we need maintenance. That's wake-up call in the U.S. After that, there's some accident in the U.S. And early part of the 70s, U.S. introduced compulsory bridge inspection. So after 40 years, they are working for the bridge management, and there's a book written by one of my friends, Yanef, Bridge Management. So that is a current situation in the U.S. Of course, there are many wake-up call in Europe. This is one example in Vienna. And even last year in Italy, we had a very bad accident. And I think more than 40 people are killed. Of course, there are many reasons. But one reason is damage in bridges, very often not visible. That's the problem. So we need a technical development. So this is a video, but I'm not sure this works. So this is a video I got from YouTube. So bridge, I think pylon collapse. I don't understand Italian, but someone is shouting. Okay, also we had the accident about 7 years ago. This is a tunnel accident, and there's a roof here. This is an air condition, ventilation roof, and this collapsed over 130 meters. Very fortunately, not many vehicles there. Only 9 people were killed. It could kill maybe almost like 100, because 130-meter ceiling roof fell down. So I think this is really a wake-up call to the public in Japan. Council of Science, Technology, and Innovation, Cabinet Office, is chaired by the Abe, Prime Minister, is the top commander in policy of science and technology. So this CSTI identified the safety of infrastructure, one of the nationally important research and development themes. At that time, 2013, CSTI proposed to conduct a strategic innovation program and 10 themes. And this is the first experience for CSTI really conduct their own project. And the 10 projects was selected, and one of them is the infrastructure maintenance. So characteristics SIP project is always, government says innovation using advanced technology. So make full use of advanced technology to enhance innovation. That's one idea. From basic research to societal implementation. So you have to develop, and also you have to implement in the society. Collaboration among ministries, collaboration among governmental institutes and universities and industry. This is a kind of my thought. 30 years ago, we are civil engineering, but advanced technology like nanobio is much ahead, very far. I feel the long distance between two groups. But advanced technology also changed. Nowadays, IT, robot, and so on. Now I feel, or maybe past several years, civil engineering infrastructure, advanced technology, rather close, like this picture. And most of the damage, as I said, is not visible. So you need some technology to identify the condition of inside structures. There are many number of the infrastructure you have to deal with. At this moment, very labor-intensive work for the maintenance work. So I thought civil infrastructure needs advanced technology very badly indeed. I should challenge to combine two technologies. And so I applied the program director position of this cabinet office, and I was selected. Another behind is that my motto, or I don't know how to call it, the attitude to the SIP or research is, I think I should follow the past president, Furuichi. He's the first president of JSCE. His speech in 1914, that's more than 100 years ago, his speech, many speeches, but one of the statements is, civil engineers are to be the leader of the leader. Persons who own the strong leadership. So that means we should coordinate many technologies for civil engineering purpose. Also, he said JSC members, probably that means who does some kind of related research, widely extend your research area as much as possible, according to your own academic interests or societal needs. But make civil engineering being the center of your research. So your research should be targeted in civil engineering. That's his statement. I like this statement. So when I'm chair of this SIP, I always keep these words in my mind. So also he says that you have to be innovative. That's, I feel this from his statement. A little bit, some explanation. Our society, Japan Society of Engineering, was founded 1879, so 140 years. After 7 years, architect group separated. After almost 10 years, electrical group separated. Mechanical group, all large group separated from this Japan side of engineering. But Fruich said that civil engineering should be the center of engineering, so we should stay as long as possible. But finally, 35 years, 1914, 35 years, civil engineer, JC separated. So we stayed, but finally we separated. But I just took this photo yesterday. The department, Cambridge University, somehow you have a department only engineering. Always everything inside engineering, civil, electrical. I feel some commonality, idea of the Fruich and the Cambridge University. I don't know if this is true or not. But this is nice, you know. One department has many programs, and the students take some common subjects. That's probably need for future development. Go back to the SIP. So 2013, end of 2013, the 10th theme was selected. Many are driven by large companies like Mitsubishi, Toyota automobile, Hitachi, Toyota. 5 are from academy and 5 are from industry. I thought that maybe cabinet office thought about the balance. I am one of them about infrastructure. So it's the idea of the infrastructure is not like a profit kind of organization. They don't create a profit, but others if you develop some technology, we can get more sales and more profit. But our group is a little bit different. So I classified 5 groups: material, robotics, inspection monitoring, and information communication. There are many engineers from outside civil engineer stay there, join this project. And in civil infrastructure management, and many civil engineers stay there. And more than 1,000 researcher engineers participate involved it. And of course, universities, governmental institute, and public and private industry. So again, he said the center should be the civil engineering. That's why I put the civil engineering group in the center of the SIP. We made a very strong steering group, and I'm here, sub-program director and members from government, industry, and university academician, robotics, electronics, civil, mechanical, control material, all these kind, including management, economics professor. I asked to join to supervise my project. And we have many, many review meetings, and some project we have to decline, some project, yes, maybe 20% of the project is we stop in the middle time. So 100 site visit. So actually, this is a distribution. I'm sorry in Japanese, but civil is half of it. The rest is non-civil. Of course, like informatics, communication, electrical, applied physics, material, even economics and business information. That's the composition of the project members. So in almost all projects, members are a mixture of civil, mechanical, electrical. In some projects, I forced them to be mixed group. And we asked the mixture of the university, government, industry as much as possible. So I thought that the good combination is very important to develop a new technology, a new system. So just to explain a little bit about some output of the project. And tunnel inspection. So we developed a vehicle which install like a camera, radar, laser, and so on. And with velocity speed 50 kilometers per hour, and they inspect all the surface of the tunnel. And after that, automatically they give the data result, so that we can go to the screened inspection. That's used for the screening of the inspection. This one is organized by the Nakamura in the Tokyo Corporation. And this is a tunnel. And they made a frame, which is movable frame. And they do, this one is a measurement, I think, the image, vision, and also the hammering. But the point is, you allow the vehicle. Usually, you close the lane so that you have a traffic jam. But you allow, they like to have the system which allows the traffic through. And actually, we did some experiment in the real tunnels. I thought police would not accept this, admit this, but actually police agreed to use this one under traffic. That's a very, I think I like this. Also, this flame moves. So one day, one night, keep going and finish tunnel inspection. A drone is very common. We have many projects in drones. And this drone is developed by Professor Ono in Tohoku University. And this drone goes to the backside of the slabs and take a photo and so on. So this is a drone photo. A drone take a photo. Another type of drone is two-wheeled flying robot like this. I'll show you the video. So this is a high bridge pier. And usually, when you inspect, you use a rope. We ask a rope to inspect this. But this one is two-wheel. So you go up and take a vision image. That's the way they inspect the bridge pier, high bridge pier. This is a bearing, steel bearing. This is a small one. So you can go up there and inspect like this bearing. So this kind of, and after that, all the information, vision information is digitized and stored in a 3D CAD model. So that's the way everything is automated. Most difficult is to implement developed technology from SIP to actual maintenance site works in especially local government. Because local government very often very reluctant to adopt new technology because there's no engineers. They don't know engineering or technology much. So we need to promote our SIP infrastructure technologies in this area, local area. How? We opened a kind of branch. I'm in Tokyo, but we opened a local branch, 12 regional branches introduced in the middle of SIP. Regional representative is mostly universities, because university, they can talk from the government people, they can talk to the private industry people, so it's a good position, we thought. So we asked the professors to promote our technology in regionally. That's what we asked. So this is Professor Rokugo in Gifu University. They have a seminar, workshop, demonstration, lectures, all these kind. Let local government engineer or people knows our technology. And sometimes we get feedback to improve our technology. That's the way we did. Some bridges in the local area is a large bridge, and it's difficult to inspect. Not impossible, but very expensive. So what we did is we asked all the participant project leader, various kind of the robot, to join this demonstration. And this is the one example in bridge in northern part of Japan. So of course, traffic is through, so not disturbed, no traffic jam. That's a very nice things about the bridge inspection. Usually, you have to close the lane and there's a long queue. So they are during inspected. So that is with a hammer robot. This is a hammer. So they have this is a drone and the contact with the backside of the girder, and they hit. And all the data is recorded here. That is a rather simple inspection pole for high roof. So they take a video, the image, and they superimpose after that. And of course, most important is what's the width of the crack and what's the density of the crack and so on. This is, again, 2 wheels robot. Our project is finished. SIP is finished this end of March, but some of the output is now actually being used in the local government. That's nice. So I finish. And as I said, some part of our structure is not, the damage is not visible. So I try to visualize the damage inside the structure. This is conducted a high-sensitive magnet sensor for steel structures by Professor Tsukada, Okayama University. His major is physics. So if we didn't have this SIP, he would not join this kind of project. But his physics, his area is physics, but he's keen to develop the sensor probe using eddy current. And to detect the cracks, also thickness of the steel plate, even with painting. The nice part of it is even underground, through the soil, they can measure the thickness of the plate. Even underwater, through the water, they can measure the thickness of the water. Usually we use ultrasonic, but ultrasonic doesn't work this kind of situation. So that's the advantage of it. Also, this is a lady, Miss Dr. Otake in science laboratory, Riken. Also, her major is physics. But she used the neutron beam to inside of the concrete to visualize. Is there any water or steel bar corroded or not? Still, this is not popular technology yet, but under development. But this is a very challenging technology. Third one is bridge deck inspection. The most vulnerable element in bridges is a slab and deck in Japan and also in the US. So cracking, segregation, cracking. If you have this crack, it's very dangerous. We would like to know whether it's crack or not. But the problem is you cannot see from outside. So usually we use a hammer technology, change the sound. But one of my students used electromagnetic ground penetrating radar with velocity 80 kilometers. Again, you don't need to disturb the traffic. I think he stayed for a while in Cambridge University under Professor Soga. So there is a reflected wave, and he analyzed it. So he used a very high level of the signal processing technology. I don't know the detail yet, but if there's a water or a crack, he can identify by very advanced signal processing technology. So this is an example of the 5-span, 6-span, 7-span bridge. So let the vehicle go 80 kilometers per hour, only a few seconds. They get all the data, analyze after a few minutes, there's a result there. Black part is sound part. Red is not so. Yellow is a relatively bad part. So this is a span, right? So this is a joint. Usually water goes into span the joint. So many yellow part is near the joint. So you can identify the damage. But we would like to know this is a real result is true or not. We do hammering and check whether is there any damage or not. And we compare the damage result from the radar and the actual hammering. And we found a very good agreement. And this kind of practice we repeat in many places to ensure the result is okay. So actually, he's one of my former students. And I give his doctoral thesis is a bit different from bridges. Rainfall monitoring of leaky coaxial cables. Leaky coaxial cable used high-speed train to communicate train and the station. So we thought the wave magnetic wave is disturbed by the presence of the water, rain. So he studied this in using experiment and theoretically. But he has to study electromagnetic theory. He has to study antenna theory. He has to study advanced signal processing, even though he's civil engineering background. So he spent 3 years to study in going to electrical engineering, sometimes other. So he's ready to do this research. He has a good background in civil engineering and also with other disciplines. So we identify the damage in many monitoring or inspection methods. Finally, we would like to know our structure is sound or what is the residual life. So this is Professor Maekawa's achievement, prediction of the residual fatigue life of reinforced concrete bridge slab. He was my colleague, one of my colleagues in the University of Tokyo. He's now working at the Yokohama National University. He has spent almost 30 years to construct and develop multi-scale concrete model, from the nanoscale to meter scale. And we are concerned about the fatigue and the repeated vehicle loading. So repeated loading, the deflection increase gradually. So I'm sorry, this is in Japanese, but the deflection increase as the number of the vehicle number of the repetition increase. So this is an experiment. This is a prediction by this multi-scale model. So good agreement. Same is like this one. This is an experiment of the number of the loading, 1 million, 10 million, 100 million repeat loading. So deflection increase gradually. Reaching up to a certain level, we judge this slab is limited to the fatigue life. Now, if you do test, backside of the slab has some cracking. So if you have a cracking this gives as an input of this slab and predict by this model, you have this overlapped. If you have more 3 million repeat load, you have more cracks. Give that as an initial condition and predict again this. More. So that means if you know the cracks, regardless of the past loading history, we can predict the residual life. That's a very amazing result. So only thing is by drone, we take a picture and digitize and give the input and predict. So we can predict, we establish prediction of the fatigue life. Also at that time, maybe 3 or 4 years ago, AI came up. So we also use, in many places, AI technology to simplify the process. So of course, many occasions this is discussed. We measure physical world in many ways, cyberspace, and we send all the data models to cyberspace, all the data, and we analyze it. And this analysis tells you the lifetime prediction or condition assessment. That is the way we should go. And this system to accurate and efficient assessment and lifetime prediction of infrastructure, its foundation, not completed yet, but foundation is completed by this, our SIP. Also, I keep saying the members of our SIP group, this is our target, better and efficient infrastructure management. To achieve this, what you need? Of course, you need the structural engineering knowledge, material, sensor, robotics, communication, informatics, all these like advanced technology. So develop the integral technologies and systems we would like to use. And if you can make it, we say maybe you did achievement, innovation. That's already keep saying that. But combination, combining various technology, maybe not all, selectively is a nice way to go. So I think it's a kind of a new civil engineering challenge. We have to produce young engineers who can integrate new technologies for civil engineering purpose. So I'm bridge engineer, but more important is not bridge. Bridging is more important. So innovation is highly expected in every area probably in the world. Civil engineering, unfortunately, often is conservative and a bit away from the innovation. So let's look at how the great engineers in the past. For example, British engineer Bruno, or Robin in Brooklyn, and Eiffel, all these great engineers. Of course, maybe for UK, in front of UK people, I don't need to explain it, but Bruno, he wanted to have a transportation from London to New York. So he built tunnels, I think it is a Paddington stations, bridges, all kinds of structures. Sometimes he was opposed to the bridge, but he convinced and made a Clifton suspension bridge. And also he needed ships to go to New York. He built, designed. So he studied various kinds of subjects, and he made it. So Bruno is incredibly versatile, very visionary, excellent in details, and challenging. So I feel he's a very innovative person. So this is with him, Paddington Station. So I heard that in BBC got some enquete some years ago, maybe 15, 17 years ago, he was number 2. I'm very proud that engineer is number 2 in the public. Another example is this. But let me see, like other, like Robert Meyer, Switzerland, or Italian, and I would like to explain a little bit about heroism from Japan. North Breakwater in Otaru, Hokkaido is now complete. It's existing more than 100 years. And this one was supervised by Hiroe-san. He's originally a steel structure person. He wrote a book in English long time ago, more than 100 years ago. But he was asked to be a supervisor construction of the Otaru North Breakwater. And he studied mechanical engineering, and he thought we should develop some machine to construct this breakwater. Otherwise, human work is too much, too many, probably endless. So he ordered the most advanced construction machine in Titan in the UK company, and very challenging, and still, of course, this breakwater exists. At that time, government says cost down. So using a volcano ash, Hiroe developed a new concrete, less expensive for marine environment. Put the volcano ash. Volcano is very cheap, right? But he was not full confident about the long-term performance, durability of this concrete. So he prepared 60,000 test pieces inside the water, and every year they test 100, make sure the strength is adequate or not. That's after that, still they are crushing the piece every year. So this is not using sensors, it's still like a monitoring. So the very new idea. So also he proposed a formula, wave force, Hiroe formula. And this formula has been used for worldwide almost like 100 years. So it's very talented. So I feel innovation strongly in his work. So I think this is the end of my presentation. Innovation is absolutely required, even like for our infrastructure management, efficient and cost down, less cost. Civil structure engineers are basically problem-oriented, wide view, interdisciplinary, communicating with other engineers. So potentially, they can, or we civil engineers, can be innovative. And the great past civil engineers, bridge structure engineer in the port, as I explained, they are very innovative indeed. And I really feel through my experience of SIP, civil engineers, half of it, they are very innovative in the SIP project too. So thank you for attention.